Hi guys, in this video we're going to take a look at the solutions to the questions asked in the Week 2 quiz. We'll start with question 6 because questions 1 to 5 you can't actually reach the end of the quiz without answering successfully. So in this question we've got an object that is thrown at an initial velocity horizontally from the cliff, and we want to know how fast that is. We know that the cliff is 125 meters tall and that the object lands 19 meters away from the base of the cliff. So we'll start by defining our positive directions as to the right and down in the x and y. And we'll write down what we know vertically about the motion. We know that the object starts with 0 vertical velocity, that it will travel a distance of 125 meters down, and with an acceleration of 9.81 meters per second squared. And from that we can work out its time of flight. So working with s equals ut plus half at squared, we get that 125 equals 0 times t, so that term's going to disappear, plus half times 9.81 times t squared. Rearranging this gives us that t is equal to the square root of 2 times 125 divided by 9.81. And this gives us that the time for the object to fall to the ground is approximately 5.0 seconds. We can now turn our attention to the horizontal motion of the object. We know that it travels 19 meters in 5.0 seconds, the time it takes the object to fall to the ground. From that, we should be able to work out what the velocity of the object was horizontally using v equals d divided by t. And we get that that's 19 divided by 5.0 equals 3.8 meters per second. Now, since the object was thrown horizontally, the horizontal velocity is the velocity that it was thrown at. So we could then state our answer as the object was thrown from the cliff with a velocity of 3.8 meters per second horizontally. Okay, so for question 7, we've got a projectile that is launched at an initial velocity at an angle, and what we know is that the range of the projectile is 260 meters and the maximum height is 42 meters off the ground. Using this information, we are asked to come up with what the initial velocity of that projectile was. So we'll start with what we know about the motion vertically. We want to know the initial velocity. We know that the acceleration is equal to negative 9.81 meters per second squared. We'd like to know the time of flight because that would allow us to work out the horizontal velocity of the object. And we know that at the end of its motion, its displacement is 0 because it's come back to the same height that it started at. That doesn't really give us enough information to work with. But what we can do is realize that we know certain pieces of information about the object when it is halfway through its motion. So what we know is that when the object reaches its maximum height, its velocity is 0, it's at a displacement of 42 meters, and because of the symmetry of the motion, the time taken to reach that point will be exactly half of the total time of flight. So working at this halfway point and using s equals vt minus half at squared, v is going to be 0, so that first term disappears and we get negative half at squared. Rearranging gives us that the time to reach the maximum point is equal to the square root of negative 2 times 42 divided by negative 9.81, and this gives us a time of 2.9 seconds. And from this, we can work out that the total time of flight is 2 times this answer, which is approximately 5.8 seconds. We can then work out the initial velocity vertically using v squared minus u squared equals 2as. This gives us that 0 squared minus uv squared equals 2 times negative 9.81 times 42. Cancelling the negative and taking the square root gives us that uv equals the square root of 2 times 9.81 times 42, which gives us the answer that the initial velocity was approximately 29 meters per second vertically. Meanwhile, in the horizontal direction, we have that the initial velocity horizontally is equal to the distance it's traveled divided by the time. And at this point, I'm realizing I've just made a slight mistake. I should have rounded that answer off to 5.9 seconds, so I've just changed that. And we've got 260 divided by 5.9 seconds, approximately 44 meters per second. So we know that our initial velocity had a vertical component of 29 meters per second and a horizontal component of 44 meters per second. So we can work out the initial velocity using its components and Pythagoras' formula as the square root of 29 squared plus 44 squared. And this gives us that the object was initially moving at 53 meters per second. Finally, we can work out the angle, and we do this by putting theta equals tan inverse of its vertical motion divided by its horizontal, 29 divided by 44, which gives us an answer of 33 degrees. So we could now state that the initial velocity of our object was 53 meters per second at an angle of 33 degrees above the horizontal. In question 8, we've got a situation where we have a catapult capable of launching a projectile at 65 meters per second, and we want to know the maximum distance that we could shoot that catapult so that it would hit the city walls of our enemy. So what we're actually going to do to solve this one is we're going to derive what's called the range formula. Vertically, we're starting with an initial velocity of 65 sine theta meters per second. Overall, we're going to have a 0 meter displacement because the projectile is going to land at the same height that it started. We have an acceleration of negative 9.81 meters per second squared, and we want to know the time of flight. Using s equals ut plus half at squared, we get that 0 equals u sine theta times t plus half times, and I'm just going to put the acceleration as negative g here, where g has the value 9.81, t squared. And I'm avoiding putting in values for u and g at the moment because I want to get a formula that will work for any value. If we factor out one of the t's, we get that 0 equals u sine theta minus half gt, all multiplied by t. Now we know that when we have two things that multiply to give 0, one of those two things must be 0 itself. So our two solutions are either that t equals 0, or that this first part, u sine theta minus half gt, equals 0. Rearranging that last part, we get that t equals 2 times u sine theta on g. Obviously, t equals 0 corresponds to our initial placement of the object, where it is at a displacement of 0, and so this second time has to be the one where it reaches the end of its projectile motion. Looking at the motion horizontally, we know that the distance that it travels, the range of the projectile, is its horizontal velocity times the time of flight. This gives us u cos theta, the horizontal velocity, times the time that we've already found, 2 times u times sine theta, all divided by g. Bringing this all together, we get 2u squared cos theta sine theta on g. But there's one last bit of simplification that we can do using a certain trigonometric identity. That identity says that 2 times sine theta times cos theta is equal to the function sine 2 theta. Using this and substituting it into the formula we already got, we get the range formula for projectile motion. It allows you to calculate, knowing the initial velocity and the angle of launch, what the range of that projectile will be. Now, in this case, we are interested in the maximum range. So what we're really asking is, at what angle do I launch to get that value to be a maximum? Now, when we think about it, sine 2 theta, sine of anything, can take values between -1 and 1. So obviously, we're going to get the maximum answer when sine of 2 theta is equal to 1. So what we get is that the maximum distance that a projectile can go, its maximum range, is equal to u squared on g. And when sine 2 theta equals 1, that corresponds to an angle of 90 degrees. If 2 theta equals 90 degrees, then that means that we get the maximum distance when theta equals 45 degrees. And so using this formula, we find that for an initial velocity of 65 meters per second, we get a maximum range of 430 meters. Alright, finally we're going to take a look at how to answer question 9, which was the challenge question and is honestly quite a difficult problem to approach. So what we have in this scenario is one guy down on the ground is going to throw a water balloon directly at his friend who's sitting on top of a nearby wall. Right as he releases the water balloon though, his friend is going to drop from the wall in an attempt to make it miss him. And the question will be, is the water balloon going to hit him or not? Now, for the friend who is dropping from the wall, his position at any time t is given by h plus ut plus half at squared. The ut plus half at squared bit gives us his change in position, his displacement, and we add to that his initial value. Initially, he is at a height h. Of course, the friend who is just dropping off has 0 as his initial velocity, so we end up with h plus half at squared. So now, knowing the height of the wall and the fact that acceleration is 9.81 meters per second squared down, for any given time t, we can tell exactly where that person is going to be. What we need to do is come up with a similar function for the water balloon. When we do the same thing for the water balloon, we now end up with two functions. So I've labeled the friend one x2t and the water balloon is x1t. Of course, the water balloon, if we follow ut plus half at squared, the initial vertical velocity is u sine theta. Now, right now, those two functions don't look particularly the same. We've got plus half at squared in both cases, but in one we've got h and in the other we've got u sine theta times t. The trick will be realizing that we've actually got more information than we think. For example, given that the water balloon is thrown directly at his friend, that means that the tan of the angle is equal to the height of the wall divided by the distance to it. What we also have is that the time taken to reach the wall, which I'm going to call capital T, is equal to the distance to the wall divided by the horizontal speed. So in this case, that's d divided by u cos theta. If we use both of these and substitute into the water balloon equation and the friend equation, then we might be able to work out exactly where both of them are at the point where the water balloon hits the wall. Working with the friend position equation, we can work out that when the water balloon hits, so at the time capital T, that function would give us h plus half a capital T squared. Substituting in what we know about that time to be d on u cos theta, we end up with h plus a times d squared divided by 2u squared cos squared theta. Let's go do the same thing to the water balloon equation. So at the point where the water balloon hits the wall, time capital T, we then have u sine theta capital T plus half a capital T squared. Substituting in for capital T, we now get u sine theta d over u cos theta plus the same thing that we had for the other one. The half at squared becomes ad squared over 2u squared cos squared theta. What we first need to realize is that in the first part of the equation, we've got a u on the top and on the bottom, so they cancel out. We've then got sine theta divided by cos theta. Now that's tan theta, and we already worked out that that would equal h on d. And we've got a d still there in the equation, plus ad squared all over the 2u squared cos squared theta. And that's going to simplify to h plus ad squared all over 2u squared cos squared theta. And would you look at that? According to our equations, both the water balloon and the friend are going to be in exactly the same position at that time when the water balloon hits the wall. And mathematically, that means that you have scored a hit.